The goal of this project was to create an AI which uses reinforcement learning to progress through Super Mario Bros. We used a pre-created clone of Super Mario Bros. That we got from an AI gym. The AI that we created interfaces with the game through simulated keyboard inputs. It is analogous to handing a robot a controller and telling them to learn to play Super Mario Bros.
So, moving on to the actual agent class. Starting out, we have the initialization of our agent. This just makes two fields here, last action, last state. This just allows the agent to remember the last action that it took and the last state that it was in, and why we need that will become more apparent in a bit. Then we also have this dictionary right here, known states. This is kind of the meat and potatoes of the agent. So any kind of reinforcement learning, at least as I understand it, is largely a mapping of actions and states to the results that come from those. So in this case, we're going to have mapping of an action state tuple to a resulting state and resulting reward tuple. And so how our agent actually learns and takes in new states is through this learning method right here. So it will have remembered its last action, its last state, and the last action that it took while in that state. And then it will map that action state pair to the state that it is now and the reward that it is getting out of that state. So that is basically how our agent learns and remembers what it has seen before. So the next logical thing that we're going to have our agent do is actually output actions for Mario to do. This is going to include something called explore or exploit, which we talked about in the reinforcement learning lectures. Basically, this just means exploring is doing random movements just to kind of see what states and what rewards we get out of them. And exploitation is actually choosing the best possible state, or the best possible action in our current state from the action state pairs that we already know. So the way that we're going to decide which one to do is we have this probability function down here. This is basically just going to say, okay, in the beginning of your trials, you're going to want to explore a lot more just to learn new paths, learn what actions will do in different states, see what rewards you can get out of our action state pairs. And then after you've learned a lot, so after time has gone by, it's going to do less and less exploring and more exploiting. So that's what this explore exploit function is doing here. Then for the actual explore and exploit functions, exploring is pretty simple. We just take the actions that we are given and choose a random one. Right. Exploiting is a little bit more complicated. So for each of the actions that we're given, we're going to loop through, pair it with a state, and we're going to check our dictionary of known states and say, hey, have we done this action while being in this state before? If we have, then we will return the reward that we got out of that. And then at the end, we will just simply choose the best reward from the possible actions that we can take in this state.
So, interfacing. The way that this works is main.py is taking in a bunch of different files and putting them together and allowing them to communicate with each other. The main source of communication in terms of how the AI is controlling the game versus how the game is running itself is based on this right here. So state.txt and reward.txt are all updating constantly. Both of them update constantly with the state and the reward, and then this pulls upon that state and reward. That then gets passed into the AI, which is agent.py. This is a brief look of it. And then that outputs a decision from this list, and then each decision calls upon main.py to take an action. Or not main.py, but actions.py. So we have our list of actions here, and we're using a package called py-input, and then py-input is used by the AI as basically a controller to control the window. This would even work if you just clicked out of the window. It would literally just be typing buttons and or typing letters. So we took some data as a way to scientifically show a more quantitative approach to how much Mario is actually learning, to kind of prove that our AI is in fact learning. And the results were pretty evident that he is indeed learning. So with the data here, it seems that at with 20 decisions versus 100 decisions versus 500, he's very obviously, the averages show that he made it further in 500 frames, or in 500 decisions, than he did in 20. So this iterator value is just how many decisions Mario gets to make. And since every time he dies, he starts back at the beginning, that's able to basically give us a control of, okay, if he's making this many decisions, we should expect him to get further in the level if he's learning. And the averages show that he is in fact learning. We're going to focus on the max frame, and that essentially means that that's the furthest he got in that 20 decisions or 100 decisions or 500. So his average furthest distance in 20 decisions was just under 5 frames, which isn't too bad, but in 100 frames it went up substantially, and it went up even more for 500 frames, which is pretty good, which is pretty evident that he's learning. But what's really evident is that it's almost a perfect logarithmic curve, which is awesome in terms of the fact that the r-squared value here is 0.9992, which means that it's 99.9% a perfect logarithmic function, which means that his learning is not only happening, but it's also super predictable.